Okay, so last, let's talk about how to use the GEM for starting some application problems. We have mentioned we can start the nodal classification or the graph classification already, right? And in the last part for the talk, we want to illustrate some other application tasks we can start it for the, with the graph neural networks. So we mentioned before, given a protein structure, we can define the protein structure as a graph structure, right, as well. So given a protein as shown here, we can define its corresponding graphs by specifying the atoms as well as bonds among the atoms together. Then the structure of the protein will be defined into a graph as shown here, right? So generally, given different proteins, we can define the graph structure in different ways, and they will have different functions or different properties, right? So one of the very important problems starting in the protein analysis is to study the function of different protein structures. So this problem can be projected to the classification of the protein graph instead, right? In other words, given the protein structure, we can define its corresponding protein graph as shown here. Then the problem we are studying for analyzing the property of the protein will be mapped to the classification of this protein graph instead, right? So by classifying the protein graph into different classes, then we can further analyze the properties or the functions of the protein structure as we show here, right? So we can classify the graph structure, of the proteins into different classes. Then we can analyze the functions, and which is very similar to the graph classification we studied before, right? Okay, so besides studying the graph neural networks, for the protein graph that we show here, we can also study this graph neural networks to analyze the brain graph as well. We know that given a brain, scanning image of the brain organ inside our head, we can have different layers of the scanning result, right? And this is layer by layer of the scanning result. So this scanning process will record the activities of different regions inside the brain, right? So according to the medical studies, for the brain, we can divide the brain into different regions. Normally, there will be a certain number of regions inside our brain, and each region will be responsible for a certain function of our activities. So by analyzing the correlation of the activities of the brain, this is scanning result, among different regions, then we can further transform this brain scanning result into a brain graph. So we can have different nodes. Each node in the brain graph denoting a region in the brain, and we also have some edges. This edge denoting the correlation among different regions in the brain in the activities. In this way, we can transform this brain image into a brain graph as we show here, right? So compared with the original brain image, this brain graph, the size is much smaller because normally this image can be very large. However, if we transform them into a brain graph, the size for storing the brain graph data, the cost will be much lower. That's the reason why the brain graph is frequently used for studying the neuroscience problems, and we transform many neuroscience problems, image data into the graph data instead. So based on the brain image, we can transform them into a brain graph. Then we can further analyze if certain people have some brain diseases or not, right? In other words, we can classify the patients based on the brain graph inputs to either the patient has some disease or not, either positive or negative classes, right? And in this page, we show you the outline of the model proposed in my group. For classifying the brain graph or brain image into different classes for detecting some potential diseases of the patient. So formally given the input brain graph, which will be something like this, and we can build a model to learn the representation for the whole graph, right? Before we mentioned we can learn the representation for the graph by utilizing the GCN or GAT models. However, here in our work, we propose another model. It's called ISONN. So we try to learn some isomorphic features of the input graph, and based on this feature, we can further classify the brain graph into either healthy or sick, and to denote the potential diseases that may exist in the brain, in the patient's brain. And in the bottom part, we also illustrated the detailed architecture of the model as well. To learn the representation of different parts of the input graph, and also learn the classification result by the feature we extract. Okay. So besides the brain graph started, and we can also utilize the graph neural networks for starting the computer vision problems, right? So before we have mentioned, we can generate some text data based on some inputs. A very similar we can start in the computer vision is to generate the caption for an input image. So formally, as we show here, we have an input image. We know that in the image we have different information. Now this man is wearing a jacket. This jacket color is red, and he's also riding a motorbike on a road. Therefore, according to the input image, we can recognize the same graph from the input image, right? Now this person is wearing a red hat, and he's also riding a motorbike. His motorbike is on the road, right? So based on the same graph, actually what we can do further is to generate a sentence to describe this image. Now, given this scene graph, we can further generate a sentence for describing this image as a man with a red helmet riding a motorcycle down a countryside dirt road, as we show here, right? Which describes the information inside this input image with one sentence. Of course, depending on the model, we can further, polish the sentence according to some model architecture that we show here, right? So this problem is called image captioning. So given the input image, we can extract the scene graph from the input graph. We can further generate the sentence for describing the image based on scene graph. This will require this graph, as the intermediate result, for connecting the images to the text, right? So besides the application to the computer vision, actual graph is more frequently studied in the natural language processing this area as well. We know that in the real world we have lots of documents. Also for the documents, they are unstructured normally. So these kinds of unstructured data are normally very hard to deal with, right? Also very costly to deal with. So in natural language processing, a very important topic we study is to study the corresponding knowledge graph instead for analyzing the documents. In other words, given a bunch of documents, we can extract its corresponding knowledge graph out by detecting the entities together with the relationship among the entities. So given documents, we can define its corresponding knowledge graph as we show on the right hand side. They cover all the entities that may be covered inside the documents. Also, they have some edges denoting their relationships according to the documents among these entities. So by transforming these kind of documents into a knowledge graph, we can further study some problems based on the knowledge graph instead by using these graph neural network models we discussed before. So compared with analyzed documents, this knowledge graph is more clean, right? Compared with text data, also knowledge graph is structured than its unstructured documents we show here. So the GM models can also be extensively applied to analyzing the knowledge graph we have in NLP this area as well. Okay, so these are general application problems we want to mention here in today's talk. We also have some more application tasks to be studied in the next lecture. We will introduce detailed architecture, how to build a GM model for studying some specific problems in the next part. Here we want to do a summary for this section. In this part, we focus on studying how to build a deep learning model for graph data, which will be for the graph neural networks, right? So we'll compare the graphs versus the images as well as sequence data we mentioned before. We also discuss the objectives for graph neural network model learning, which is to learn the embedding vectors for all the nodes inside graphs, right? We will discuss the SGC operator for the GCN, and we mentioned what is SGC operator and how it works, and how to use this SGC operator for build a GCN model. We will briefly mention the GAT model as well. Potential problem with the GCN model in the information integration or aggregation, and what is the difference of the GAT model architecture, and how do they address this problem, right? In the aggregation process. Finally, we can show some potential applications with the GM models. We show some examples. How to build a GM model for classify the nodes, for classify the graphs, and also for studying some other interesting problems with the GM model. We will have something more to be discussed in the next class for the applications of GM models. So here is some task for you to do after class. For the readings, please read the GCN paper as well as the network embedding paper. Also, it's time for you to move to the last stage, stage 5 for the project on deep learning for graph learning. So the task to be studied for the stage 5 will be for the lower classifications. In other words, given the graph inputs, we want to build a GCN model to classify the nodes in the graphs into different classes. Then we can learn the model. And we will provide with both dataset as well as some descriptions for the task. And we also provide you with some links for the GCN source code and the GAT source code from GitHub. They are all based on PyTorch. If you are interested in them, you can also further check them by yourself after class to see how they work.